All right. So I want to pick up with a handful of questions that are going to reiterate what we talked about yesterday. Now, hopefully you've recognized this through the last 100 days of class or more, that I'm not all that concerned with getting through 10 examples of this. I'm interested in us being able to do 3 or 4 of them and understanding all the different dynamics of the relationships that exist within these triangles, okay? Because if we can do that, we can understand all the relationships with 3 or 4 of them, then when we get to the 5th one, 6th one, 7th one, it's instinctual on what we're supposed to do, why we're supposed to do, and that kind of thing. And then when we get stuck on a particular problem, we know how to get ourselves unstuck, okay? Because we understand how this stuff is all intertwined, interrelated, and how it's working together, okay? So as we go through this, a couple things I'm going to show you. We're going to use RTI 83, 84, or I'm going to use Desmos predominantly, but there's going to be times where, you know, we're working inside the same triangle, finding 4, 5, 6 different values and trying to relate them and kind of explain maybe the purposes of the approaches we use. So kind of keep that in mind as we move on. This first one, all we're going to do is I'm going to put 2 variables up here. We've got x, and we've also got, eventually I'm going to solve for this one down here, but let's, I guess, skip that for now. Let's just go ahead and see what we've got going on right now with this one. If I've got these 3 parts, okay, we talked about yesterday that in every time that we see that this only works in the right triangle, we see that we've got an angle measurement that is different than 30, 60, 90, or 45, 45, 90. We're going to use this tool. Okay, we're going to use SOHCAHTOA, correct? Okay, so we have SOHCAHTOA. If I look at that being the angle, okay, we want to identify then the side that is opposite that angle. You guys agree that this CA would be opposite? We talked about yesterday how it's, you know, if this is like an eyeball, it's looking at that side, right? Okay, so that's opposite. What would X be? Hypotenuse, and 11 then adjacent. Okay. So now we have got enough information to actually deal with all 3 of those trig ratios. Whenever I'm working in a right triangle, all of those ratios exist, but based off the information that we have, only one of them is going to work. What I want to do right now, I don't want you to write anything down, just kind of watch, and then I'll tell you at the end what you can write down. If I go SOH, S-O-H, so that's sine, right? And it's sine of the angle that I'm interested in, equal to now, opposite. Do we have, this is the opposite side, right? Is there anything written here? No. No, so it's going to be blank. Over hypotenuse, which would be x. If I've got an equation there with an object, a position, and a fraction that is blank, it's ultimately like there's another variable there. Does that make sense? Like maybe I put y there. Would that be a problem solving that equation if I had 2 variables? Yeah. So sine, even though we can apply it in a triangle, because of what I'm providing, what I have, doesn't get me anywhere in this question. Okay. So then, working on that one, cosine of 37, that's adjacent. So adjacent would be 11, and hypotenuse would be x. Does that one fill in all the parts? Yes. Yes. So that one, because it fills in all the parts, only one of those parts is a variable, that one's something we can solve. Okay. Let's look at tangent. Before we finish, tangent of 37 would be opposite. Again, that's going to be blank there, right? Over adjacent, which would be 11. So there's a situation where even though we can use opposite over adjacent, or we can come up with a relationship of opposite side divided by adjacent side, because we don't have anything written down as the opposite side, we can't really use that one. Okay? So we only deal with the cosine one. Okay? Now the reason I go through that is because I want you guys to understand some of the phrasing that I'm going to use as we work through this topic. I want to ask you a question like, what sides do they provide you with, or what sides do you know something about? And in this case, you know something about the adjacent side and the hypotenuse, right? You know absolutely nothing about the opposite side. So when answering that question, what sides do you know something about, that's going to tell you, when you answer that, that's going to tell you whether I use sine, cosine, or tangent. Here you know something about the adjacent and hypotenuse. Okay, so we know then we're going to use cosine, and that's why this formula here got generated. All right, so that is always a proportion. I can cross multiply, can't I? So I get 11 is equal to, now I'm going to write it this way first. And I'll talk about in a moment why that's kind of maybe not the greatest thing to do. But if I do it that way, the reason I want to write it that way first, anybody know what cosine 37 actually is? Okay, so you just read off some random decimal, right? No, it's not random. All right. That one right there, right? 0.798. So that is actually what this symbol is standing in for. 0.798635510047, and that actually goes on forever, okay, times x. So what would you do to both sides of this equation if you were trying to solve for x? Yeah, you would divide by that number, right? Well, what I'm trying to get at here and explain is that number right there is just a coefficient, okay? And when I try to isolate x, I try to get that coefficient to be 1, don't I? So let's wipe out. Come over here, divide by cosine 37. So now I have x equals 11 divided by cosine 37. And we type that into our calculator and we get our distance. Okay? Now here is the way that we traditionally talk about, oh, wrong button, cosine 37. So that's that distance. We had 11 equals, I wrote it as cosine 37 times x, right? If you put parentheses around your argument here, around that angle measurement, this is perfectly fine to write this way. The further you get into trigonometry, those parentheses, especially like the upper level math textbooks, you get to like a college textbook, they'll write cosine 37 this way. Okay? So now if I put x on there, do you see how it could mean that maybe I've got a parenthesis there where I really want it, or there, and that would be different. Does that make sense? Okay? So in order to eliminate that, you heard me say this before, that ambiguity of whether that x is on the, inside the parentheses or not, we usually put that out in front. And now if I write it this way, is there any question of whether that should be part of the angle or not? No, it's out front, right? Does that make sense anyway? So you're going to see a lot of times it written that way, x cosine 37. The cosine 37 is still just a coefficient. Yes?
So the cosine, like on the second part of the, what we call multiplying?
Yes.
We're just dividing by cosine on each side?
Yes. So right here?
Yeah.
So yes, so this was 11 equals cosine 37 times x.
No, I just wasn't sure what the cosine 37 was on the bottom.
Yep,
I thought that was, you were just taking
because I'm dividing it because I'm trying to get that to be 1, right?
Yep.
So I need to divide it by itself. And so I do that to both sides. Ian?
How do you get cosine 37 equals 11 over x?
So to get to this here,
Yeah.
I cross multiplied. So I took 1 times 11, and then that times that. Are cool?
Yeah.
All right. So now, guys, here's where I want to take this process. So a lot of your homework questions are going to be like that, and you're going to stop there and you're going to be done. Okay? But I need you to understand more of this stuff and more about this stuff, because when you get to the end of course exam, they're not giving you problems like this. They're asking you questions about relationships. Ask you not so much quantitative questions where you're doing calculations, but qualitative, the understanding of why and how and that kind of thing. Some of the questions are targeted towards that. So I want to look at this maybe in a couple different ways. We just said that's about, if I round up to approximately 13.77, right? Okay. Let's find this distance here. Let's find y. When I'm going to find y, it's obviously opposite side, right? So I need to use one of my trigonometric ratios that has opposite side in it. So it's either sine, because it's got opposite and hypotenuse, or tangent, which is opposite and adjacent, right? Which one do you think would make more sense here? Opposite and adjacent. Why? So you're telling me I've got to use y in 11, right?
Well, it's because you didn't round out.
Okay, so 11 is an exact value, right? There's absolutely no rounding there. If I would use 13.77, we're going to go through and do it both ways. We'll use it tangent and use 11, and we'll use sine and use 13.77. But if I use that 13.77, that's a rounded value. Okay, so I cut off that. So I'd have 0.0034922397 that I cut off, right? Just chop that off and let it disappear. Well, when that value gets run through another function, another operation, that chopped off amount starts getting compounded, meaning it starts getting bigger and bigger and bigger. Does that make sense? And that can be problematic in regards to trying to find the most accurate answer for y. Okay? And if you think about that kind of stuff, that's maybe one of the, for you right now, if you're taking chemistry or something like that, it might be one of the most applicable reasons for understanding why we have sig figs. Okay? For that reason. So everybody chops the same thing off, and we're all then doing the work where our error is the same, so that you don't chop off 3 decimal places and I chop off 10 decimal places. My error is much more minimal than yours is, and that's because I use more decimal places. Does that make sense? But if we all have rules that we said, based on the numbers that we use, we all chop off the same amount, the error from calculation 1 to calculation 2 to calculation 3 done by 3 different people is the same. Okay? Now, when we look at, so I want to find y. I want to go tangent of 37 is equal to opposite, so y over adjacent. Opposite over adjacent, right? That's what 11 is. I erased it, but the 11 was adjacent side. Again, same strategy. It's a proportion. You're always going to see these. I cross multiply. I get 1y is equal to 11 tangent of 37, correct? And that's really nice because y is already solved for. So previously in the last example when I solved for x, I had to do one more step, right? Some of these you're going to have to do one more step. Some of them just generate the variable right away. And it's essentially depending on where this variable is. If that variable is in the numerator, your cross product is going to automatically give you your answer. If the variable is in the denominator, you got to do that one more step of dividing by whatever your coefficient is. So I type that in. I'm going to get 11 tangent of 37, 8.28. So that is the exact value. Okay? As many decimal places out I can, that's what we're looking for y. Does that make sense? Yes.
So what's the difference between, like, the value of cosine and the value of tangent? Because, I mean, they're the same thing between this and that, like the first one that we did in this one, except for the cosine and tangent. So I just don't understand, like, what the difference between those are.
Say again?
What is the difference between cosine and tangent? Like, the values of them.
So how are you seeing that they're the same?
Oh, wait, no. Oh, okay, no. Never mind.
You see how one's on the bottom?
Yeah.
Is that what you're saying?
No, it's just I forgot it was 11 over cosine 37.
Okay. And we'll get into talking about that relationship a little bit more, maybe towards the end of the period. You start to see these links between these things. So 11 tangent 37, that is using exact values, and that is the best answer to however many decimal places I want to go for y. Okay? But because this is an option at some point, and you'll have to make this distinction of whether it's appropriate or not. Okay? What if I did want to use that side? Obviously, I got to use that. What is 13.77 called? That's the hypotenuse. So doesn't that mean I've got to go sine of 37 is equal to my y value over 13.77? If I cross multiply there, I get y equals 13.77 sine of 37, right? That makes sense? Okay. So 13.77 sine of 37. Look at the two answers. That's the best one right there. That's one using rounded values. Are they pretty close? Yeah, they differ out at the thousandths place. Okay. Let's take and subtract them. Let's go. Let's take that number minus that number. Oops. So that one minus, so it's going to be backwards, but it doesn't matter. Control C. That one. I get that number right there. Okay? And as a percentage, move the decimal place to the right 2 spots, it's 0.2, right? 0.2%. So it's a 0.2% error. Does that make sense? In regards to the 2 different ways of doing the problem. Okay? So what my argument is 0.2% very much? No. So the error there is negligible. It's marginal. Okay? The bigger that error is, I guess the more drastic I round the 2 values, like the 13.77, if I round out to 13.8, that 0.002 number gets bigger, right? Okay. Let's think about applications for this. If I'm using this stuff, using sine, cosine, and tangent to use indirect measurement because I want to go to Lowe's to buy some lumber for some project that incorporates, I don't know, a hypotenuse or one of these lengths or something like that, I could probably be okay with that 0.002 number, right? That difference. I'm okay with that, okay? But if I'm working for NASA, okay, or United States government, and I'm putting satellites into orbit that are going to use GPS to track people and objects and things, I probably want that to be as minimal as possible in that error. Does that make sense? Because that 0.2% in error might correlate in GPS to your position being off by 6 meters. What's so bad about that? Okay, people that go skiing have GPS usually on them because, so I'm like skiing in the Alps or something like that, right? They have GPS on them because if there's an avalanche, people have to come find them, right? Yeah. Okay, avalanche, you're buried in 4 feet of snow, and I'm looking for you. I'm using a pole to stick down in the ground to see if you yell ouch when I hit you. Okay, and I've got GPS tracking you, but it's 6 meters off. Am I going to find you?
First off,
maybe not.
Okay. Second off, I would not be buried underneath some off.
Okay. So the argument is, if for some reason I'm trying to use these values in a system like GPS or rockets or something like that, that there's a lot at stake, right? There's probably not a lot at stake if I'm trying to build a swing set at my house with lumber from Lowe's, right? I can be off a little bit. But if I'm doing something a little bit more intricate, I probably don't want these rounded values. Does that make sense to everybody? Okay? So it's all about your application. It's all about the context of the problem, your application, of whether, does it seem like it might be okay to use 13.77? I don't know. Okay? Let's say that we're on Math Excel. And of course, again, my college trig class does this. Like, that's the best answer. So it'll tell you, find the best answer and round it to the thousandths place. So we'd round that to 8.289, right? And in the background of, it's called WebAssign. It's just simply like your Math Excel. There's a code that says, here's the answer, match up the user's input to this answer. Well, if I did it using 11 tangent 37, I'm going to match up to what they've got in the background, right? Yeah. But if I go down to the other one and I go 8.287, because I round, right? Is that going to match up to the 8.289 that they got in the background? No. Am I wrong in my work? Yeah. I mean, I've done the procedures correct, right? I just chose maybe poor values. I had better values to pick from than the ones that I used. Does that make sense to everybody? And as we work through the rest of the year, that's something to think about. As you get to the end of course exam, that's something to think about. When you get to Algebra 2, it's something to think about. Is it okay here in this situation to use a rounded value? Or because I have the option, I have the ability to use non-rounded values, those are better, right? Okay. Just kind of think about that, okay? Can I use the Pythagorean theorem once I'm done here to see that I've done everything right? Yeah. If this is 11, that's 11. We just said this was 8.289. Okay, take 11 squared, add to it 8.289 squared. That should equal 13.77 squared. Now, obviously, it's going to be, based on rounding again, a little bit off. I would take, so take those two numbers, square them, right? And I get 13.77 squared. Okay? Are those a little bit off? Would you agree, though, that they're pretty close and that the difference in them is attributed simply to the rounding of the 8.289 and 13.77? So that can guarantee you, if you're uncertain about whether you've found the right X's and Y values, use other geometries you know about to provide validity to your answers. Okay? Huh? All right. Let's do another one. Huh? Let's do this one. Why don't you guys take a minute and see what you come up with for X. See if you can go through SOHCAHTOA to solve for X. Because I told you to.
Oh, shoot. I was kind of lost through. It's a 369 triangle. Right. What does that mean?
All right, so using SOHCAHTOA, that angle there would provide me with this being opposite, this being adjacent, and that being hypotenuse, right? So which one would I use to solve for X? Cosine. So I'd write cosine of 60 degrees is equal to X over 11, right? Cross multiply, I get X equals 11 cosine of 60. Type that in, and what do we get? Well, mine's not. When I delete my stuff, it goes back to the radians. So 5.5, right? Okay, so 5.5 is that length using SOHCAHTOA. Let's go ahead and see if we can find Y here. That would be opposite, right? What uses opposite and hypotenuse? Opposite and hypotenuse? Sine. So I'd say sine of 60 is equal to Y over 11. So 11 sine 60 is equal to Y, right? Let's evaluate that. 11 sine 60 gives me that number. Correct? Okay. Now, you just solved that. We call it solving the triangle because we now know all 6 parts, right? We know 11 over 2, or 5.5. We know that 9.52 number, and we know angle A is going to be 30 degrees, correct? Okay, so we solved the triangle. That's what it means. You might see that in your homework. It says solve the triangle. That's only the directions you have. That means find all 6 parts. Okay. Now, Alex, tell us what you were going to do.
I was trying to do a 369 triangle for the hypotenuse of the
Okay, so that, right?
Yeah. Well, adjacent angle would be 50.
Okay, so he's saying this would be my 2 in, or my largest side, right? Divide by 2 to get in, which is across from 30. Will be that, right? Is 11 over 2 then is 5.5? Yep. Then what would I do with that number to find out AC? I would multiply by a radical 3. So now I'm going to look at that and say, okay, well, that number right there is not this number, right? Or is it?
Yeah, it is.
Does that make sense? So what I'm trying to get at here is that when you come across a 30, 60, 90, or 45, 45, 90, you have the ability to use SOHCAHTOA. It will work. SOHCAHTOA works for any right triangle with any measurements that you ever come across. Okay? But pay attention to your directions, because if we're in a test or a quiz for this chapter and this picture shows up and it says find X, and it says, or let's say it asks to find AC, but it says write it as a simplified radical, okay, or a reduced fraction or something like that. Can I type in that 9.526 number? Can I type in 11 sine 60? No, I have to type in 11 radical 3 over 2, right? And you have no way of taking 9.56279444163 as a decimal and working backwards to find that 11 radical 3 over 2. Okay? I have absolutely no idea how you would do that. Okay? Does that make sense? Okay? So the purpose of them showing you, a lot of times when they ask you about 30, 60, 90 triangles, you see that in your picture. Always glance at the directions of how they want you to write your answer, because that might then dictate whether you can use SOHCAHTOA or whether you should use special right triangles. Okay? Give you a harder one? I mean, they don't get harder than this. None of these are out of the realm of possibilities in regards to. I mean, I guess. They're all very pattern oriented, aren't they? Okay, we're gonna ask.
So what do you do to find like that, like the other side? It's not like a 90-degree triangle.
Okay, so you're saying if I've got a triangle that is not a right triangle, how do I go about? So there are some, and it's all about chapter 7. It's all about the similarity that exists in chapter 7. There's some properties that we can go through and develop what we call law of sines and law of cosines, and there are formulas that will allow us to do that, and we'll get to that at the end of chapter 8. So it'll show up, but it incorporates some of this stuff along with stuff from chapter 7. Okay, so let's do this one. I want you to solve for X, and then, actually, well, let me see here. What I want to do. Go ahead, go ahead and do that one, Soft Fred, since Trey already started. No, you don't have to. Fantastic. All right, so when we set this up, which trig ratio you're going to use? Okay, so we got opposite here. This thing becomes the hypotenuse. We're going to go sine of 57 equals 10.8 over x, right? Did you end up with x equaling 10.8 divided by sine of 57? Okay, so that's great. Let's go 10.8 divided by sine of 57. Gives you that number right there. You guys get 12.877? Okay. Now, did anybody, actually, let's do this. Go through the process again, but use angle A. Use angle A instead. Do you know angle A?
Yes.
What's angle A? 33. 33. So go through the process and find the answer for x using angle A being 33 degrees. Can I? Yes. But if I use, just so we're on the same page, if I use that as 33, is 10.8 my opposite side anymore? What is it? Adjacent. So now which trig ratio are you going to use? You're going to use cosine, right? So cosine 33, what's my adjacent side? 10.8, right? Over x. You said it, not us. Did you get that? Oh, I keep going 37. I'm stupid. That was mean. So if I type in 10 divided by cosine of 33, oh, so it's 10.8. What do you recognize? Same answer. Okay. Look at the two fractions. Very similar structure for the fractions, right? The only thing that's different is sine changed to cosine. And then the angle, 57, and the angle 33 changed, right? But think about 57 and 33. 57 and 33 are, if they're angles, together they're identified as what kind of angles? Not supplementary. Complementary. What is the first two letters of complementary? Co. Co. What's the first two letters of cosine? CO. Do you see how sine and cosine are the same word except for the CO? I just told you this yesterday? Okay, so they're complementary, right? So that's the idea behind this. So what I'm saying, guys, is if I have the sine of, give me a number real quick, 55, okay? Then I should be able to take the cosine of its complement, which would be just so let's go 90 minus 55. Do you see how those two numbers are the same? So sine of an angle is always equal to the cosine of that angle's complement.
Why didn't you just put 35?
Okay? I can't do that math. Okay? So let's do this. So this is ultimately the reason I wanted to do that. Because what if I make that T and make that T, add a slider that goes between 0 and 100, or sorry, 0 and 90 degrees. Okay, I don't want to be over 90 degrees because this difference then would be negative, right? So let's look at those. Are those no matter what I have in there? So right now I'm saying this is 15 degrees and this would be 75 degrees, right? Do we see the values to be the same? Okay, and I can keep doing that. Okay, so now I'd be at 80 degrees and this would be cosine of 10 degrees. Okay, sine of 80 is equal to cosine of 10. Does that make sense? Yeah. So that's, obviously, at the beginning I talked to you about going through a handful of these questions and really understanding all the dynamics of these questions, right? Because, and I'd rather you understand this relationship because on the end of course exam, they might ask you something about that. They might say sine of 12 is equal to this number. How can I rewrite that or explain that with cosine now? 90. Yeah, you say cosine of 90 minus 12, right? And then you have that solution, that answer, where I think if we just practice on being robotic and I show you the steps for solving the triangles, you don't pick up on that. Does that make sense? and we have to be able to talk about that relationship. All right? Does that make sense? Okay.
So hard last year, and it's actually really good.
There is, did I talk about the relationship about sine and cosine yesterday?
Yeah.
And tangent?
I'm not saying.
Okay, so let's take this. Let's say tangent of 30. Gives me that number right there. Now I'm in radians. So let's put in degrees. Tangent of 30 is that number right there. Okay? Tangent, what we end up finding out about trigonometry is that tangent is equivalent to this. Do I get the same number? Okay, so tangent is actually the quotient of sine and cosine. Okay? Which is nice because what that tells me then is that I don't necessarily need to memorize anything for tangent ever as we work through trigonometry. All I need is to know sine and cosine. And if I ever, for any reason, need tangent, I just divide the two sines and cosines that I have. Okay. Another relationship that is actually up on the smart board, or sorry, the whiteboard up there. Let me get some room here, and we'll get it up here so we can record it. In your homework, you might see one or two questions doing this. Okay. If I were to take, so we talked about yesterday that sine of some angle is equal to opposite over hypotenuse, right? Well, if I take the reciprocal of this, I have hypotenuse over opposite. Okay? That would be equal to the reciprocal of this. Does that make sense? So I'll find that reciprocal, which would be 1 over sine of A. We never refer to it as 1 over sine of A, or name it that way. We like to do our algebra with 1 over sine of A, but traditionally, in trigonometry, we never write or say the phrase 1 over sine A. If I ever come across 1 over sine A, we rename it, and we call it cosecant of A. All right, and it's weird, but cosecant is what we call it's CSC there. It's called the reciprocal of sine. Okay? So when they tell me in my homework tonight that sine of some angle is 2/3, and then they want to know what the cosecant is, by definition, these two things are reciprocals, right? Yeah. So if this is 2/3, what's its reciprocal? 3/2. Okay? All your other functions have that relationship. So 1 over cosine of an angle, we call that secant. And we abbreviate it SEC. Okay. The reciprocal of tangent is an easy one. We call that cotangent. I think secant and cosine are hard to remember that they go together. Sine and cosecant are hard to remember to go together. I just remember the ones with S's do not pair up. Okay, so sine is never going to get paired up with secant, so it must have to go with cosecant. Cosine is never going to get paired up with cosecant, so it must have to go with secant. Does that kind of make sense? Cotangent. Essentially, when I'm pairing these up as reciprocals, the first letters of the names never get paired up, and that should allow you then to get them correct. So what we're saying here now, your TI-8384 does not have this button. None of your calculators have the secant, cosecant, cotangent buttons because it would take up space physically on your calculator, right?
Pardon the interruption, but concert band students, please report to the auditorium. Last period, again, concert band students, you are going to report to the auditorium today. Thank you.
All right, so here's the idea. So sine of 30 is 0.5, right, or 1 over 2? Okay. Your calculator does not have a cosecant button because it would take space up in the manufacturing of that calculator and all that kind of stuff. But your Desmos or GeoGebra allows you to type in CSC for cosecant. And if I type in 30, look at the number I get back. 2, right? Is 0.5 or 1 over 2 the reciprocal of 2 over 1? Or vice versa, right? So cosecant is the reciprocal of sine, but sine is also the reciprocal of cosecant. Does that make sense? 2/3 is the reciprocal of 3/2, right? Isn't 3/2 the reciprocal of 2/3? So it's a two-way street when we talk about reciprocals there. On your TIA 384, if you want to find out the cosecant of an angle is, you type in 1 over sine of that angle. Okay, and it'll evaluate it for you. So if I want to see that 2 show up, I type in 1 divided by sine of 30, and it will give me my 2.
Why does blue equal 10? If you do this, go over to color, blue equals 10.
I don't know. All right, so your homework, guys, is open.